So finally, let us review advantages and disadvantages of lasso over ridge regression, right? So both are regularization techniques. So both penalize the loss function by adding a term that kind of that becomes large if the model is too complex, in the sense that if the model's coefficients are too large. Both algorithms, lasso and ridge regression, they have a hyperparameter lambda, whose value is to be in practice is found by cross-validation. Well, in both models, so after we found the optimal value of lambda by cross-validation, we retrain the model with the selected value of lambda on the whole training set. So recall that cross-validation, if say we use a 5-fold cross-validation, it means that we're going to train 5 models. Each of them is going to be trained on 4/5 of our training data, right? So in the end, of course, once we pick the optimal value of lambda, we retrain it on the whole training data. So both techniques can be applied to classification problems. So until now, I've been talking about regression problems, but of course, without any change, we can apply these techniques to classification problems. So recall that for classification problems, we have our logistic regression, and we have our binary cross entropy loss for the logistic regression. So this is the loss function for the logistic regression. So basically, by adding either term, so either beta, the sum of beta j squared, or the sum of absolute values of beta j times lambda, we change it into a ridge or lasso, well, classifier, right? So this is the loss function for the ridge logistic regression. Well, this is not a regression, this is rather a classification, and this is the loss function for the lasso logistic regression. So in both cases, we can find the minimum of the loss function, and this is how we train our models. So the advantage of the ridge regression over lasso is that it is easier to train it, right? So since the loss function is differentiable, and we can just solve the first order conditions in the explicit form. So the advantage of lasso over ridge regression is that it is capable of variable selection. So it does regularization and variable selection at the same time. Now, I would like to explain why lasso does variable selection while ridge regression does not, right? So let me give you some idea, right? So we're going to reformulate these both algorithms a little bit, right? So we are going to minimize the residual sum of squared subject to either a quadratic condition or this kind of absolute value condition, right, for lasso. So now, for the sake of this example, I'm going to use p equals 2, right? So p is going to be equal to 2. So I'm going to use p beta 1 and beta 2 as my variables, and the dimension 2 is needed just so that I'm able to plot everything, right? So I'm going to introduce coordinate axes beta 1 and beta 2. So I'm going to do it for lasso and for ridge. So I'm going to draw 2 copies, beta 1 and beta 2. All right, so this is going to be ridge, and this is going to be lasso regression. Okay, so the next thing that I'm going to do, I'm going to draw this condition. So in the ridge regression, so the condition is beta 1 squared plus beta 2 squared is less than or equal than s squared. Geometrically, this is the interior of a circle of radius s, right? So centered at the origin, right? So this looks like a circle. Well, this is a solid circle. Now, for the lasso regression, right? So sorry, for lasso, we have the condition beta 1 absolute value plus beta 2 absolute value is less than or equal than S. So the set of points on the beta 1, beta 2 plane that satisfy this is a square. This is what it looks like. I mean, it's very easy to understand, right? So because if both beta 1 and beta 2 are positive, then we can get rid of the modulo sign. So it's going to be a straight line. And because of the modulo sign, this is supposed to be symmetric by changing the sign of either beta 1 or beta 2. So this is how we know that it's this square. Okay, now, so further, I have my, in both cases, I have my residual sum of squares, right? So I'm going to denote it as L of beta. This is just L, the mean squared error from the linear regression, right? So, and suppose that the minimum value of this L of beta is beyond these regions for lasso ridge regression, right? So it's going to be here, let's say, right? So this is, so here is the is beta that minimizes my loss function, right? So this is all right. But then my mean squared error. So as a function of beta, it is a quadratic function, right? And its level curves, or in high dimension is going to be level surfaces, are going to be ellipses, right? So level curves are going to look like this. So, and notice that within the shaded region for either ridge or lasso regression, we are not able to find the minimum. So the minimum is outside, right? So we need to find the best approximation to the minimum. And well, these level curves, they look like ellipses, right? So it could be like this ellipse, this ellipse, this ellipse, and basically by kind of moving further and further away from this point of minimum, so we are just increasing it. And you can imagine that we try to increase it until we hit this shaded region, right? So it looks like this. And once we hit this shaded region, the point at which this level curve of the mean squared error touches this shaded region, we found our solution to the lasso problem or the ridge problem, respectively, right? So here is the solution of the ridge problem, and the same thing is going to be true for lasso problem. And notice that the difference is that for lasso problem, and it's kind of geometrically is pretty intuitively clear, right? So that very often the solution to the lasso problem is going to happen at one of the corners of our square. And at this corner of our square, beta 1 is precisely 0. While here, beta 1 is not exactly 0. It's a small negative number, right? So here, beta 1 is not 0. And if you think about it, then, you know, for ridge regression, it has to be a pretty big coincidence, so that this solution to the minimum problem is going to be exactly at one of these 4 points. It's just because this circle is convex. But, you know, if we have a square instead, then we have a high chance that it's going to end up at one of the corners. And this is basically the reason why lasso is capable of variable selection, but ridge regression is not capable. So sometimes people kind of mix the two of them together. So, and this is called elastic net regularization, right? So this is a combination of ridge and lasso regularization terms. So here, if alpha is 0, we will get ridge regression. If alpha is 1, we will get lasso regression. This is going to be important in the computer lab. So because in R, we just have this elastic net, and if we want to extract a ridge or lasso from this elastic net thing, then we need to use to specify the value of alpha. When we train this elastic net regression, so we use cross-validation to select both optimal values for alpha and lambda. Now, in practice, this method is invented to address some shortcoming of the LASSO algorithm. Now, in my experience, using this elastic net regularization for simple linear models does not really make a lot of sense. For simple linear models, you can just use LASSO. But this elastic net sometimes becomes very useful for more complex models like artificial neural networks. And that's where we can really make a good use of it. All right, so this is all for today's lecture material. So please do the quiz, and then I'm going to summarize and wrap up after the quiz.